Thank you very much for the invitation, and thank you to everyone for coming. So I'm speaking today on anti-concentration in Ramsey graphs and a proof of the Erdös-McKay conjecture. And what I'm talking about today is joint work with Matthew Kwan, who's at IST Austria, Ashwin Sah and Mehtaab Sawhney, who are also at MIT. Okay, so many of you probably heard of Ramses Theorem, which is an important classical result in combinatorics. And very roughly speaking, it states that every large graph must contain a large vertex subset U, so that within U there are either edges everywhere or no edges at all. So let's try to be a little bit more precise about this. So a more precise version of the statement is, if n is sufficiently large with respect to k, then in any graph on n vertices, one can find a set U of k vertices, so that either every pair of vertices in U is connected by an edge or no pair of vertices in U is connected by an edge. So we can find, if n is large, then within any n vertex graph, we can find this nice subset of k vertices, which looks very nice in the sense of having either all edges or no edges at all. Okay, and here's an example. So here in this graph on 6 vertices, so you can take any graph on 6 vertices, but in this graph on 6 vertices, we can find 3 vertices all connected by edges. And that's not possible in any graph on 6 vertices, of course, but in this example, for example, we can find 3 vertices with no edges in between at all. So the point is, whatever graph you take on 6 vertices, you either find a triangle or 3 vertices without any edges. Okay, so just to make this a little bit shorter, to say a subset of vertices where all edges are present is called a clique, and a subset of vertices without any edges is called an independent set. And so then we can restate the theorem that if n is sufficiently large with respect to k, then any graph on n, in any graph on n vertices, we can find a clique or an independent set of size at least k. And so that was proved by Ramsey in 1928. And even though this result is almost 100 years old, the quantitative relationship between n and k is still not really completely understood. So basically the question is, how large do we actually need to make n with respect to k for this to hold? So that's called the Ramsey number of k, this kind of minimum threshold for n that we need for this theorem to hold. Or in other words, we can also rephrase the question the other way around. We can ask, for given n, how large can one make k? So basically the question is, how large a clique or independent set can we actually always ensure to find? So just to come back from the example from the last slide, if n is 6, so if we have 6 vertices, we can always find a clique or independent set of size at least 3, but we can't always do it for size at least 4. Okay, and so this question is still open, and it's one of the most fundamental problems in extreme combinatorics. Okay, so here are kind of the known bounds. So Erdös and McKay actually just a few years after Ramsey proved this result, proved with an inductive argument that we can always take k to be a half log to n. So they proved that if for every n vertex graph, we can find a clique or independent set of size at least a half log to n. Okay, so that gives us a lower bound on the k that we can always ensure to, for having a clique or independent set of size k. And up to this constant factor of a half, this bound is actually best possible. So this logarithmic term here is indeed the correct behavior. So a few years later, or about a decade later, Erdős proved the following upper bound. So he proved that for every n at least 3, there exist n vertex graphs with no clique or independent set of size at least 2 log to n. Okay, so it's always possible to find a clique or independent set of size at least a half log to n. And there are graphs where we can't find a clique or independent set of size 2 log to n. But so that means there's still a gap here in terms of this constant factor, whether the half is right, the 2 is right, or something in between. And so closing this gap between these constants, a half and 2, remains a kind of fundamental open problem in extreme combinatorics. So in some sense, it sounds like this isn't really a big deal, it's just a constant factor. But if you write it the other way around, if you ask about what's the kind of n that you need with respect to k, it's kind of a difference between square root 2 to the k and 4 to the k. So the gap sounds bigger, but I mean, it's the same thing. So basically, the question is, what's the correct base in the exponential behavior of the Ramsey numbers, or phrasing it this way, kind of closing the gap between this half and the 2 in front of the log. Okay, and so this is really a very important problem, but despite, and there's been a lot of research on this problem, but despite of this, over the past 70 years, there's been no progress on improving either of these constant factors. So there's been some improvement to the lower order terms, but not to this kind of main constant factor here. Okay, so here's again this upper bound theorem. So for all energies 3, there exist n vertex graphs with no cliques or independent sets of size at least 2 log 2n. So that's the kind of bound we saw on the last slide. And so Erdős proved this result with a probabilistic method. So, so more precisely, he showed that if you take a random graph on n vertices, typically it has no clique or independent set of this size. So what does that mean, a random graph? So you take your n vertices, say labeled from 1 to n, and then for every vertex pair, you decide with probability half whether you put an edge or with probability half you don't put an edge. So basically you throw a coin for each of these potential n choose 2 edges that could be there, and for each of them you throw an independent coin whether or not you place that edge. And so that gives you a kind of random graph, and typically with kind of probability tending to 1, it will be the case that this graph doesn't have a clique or independent set of this size. Okay, and so in particular, you know that there exist n vertex graphs with no cliques or independent sets of this size. However, this proof does not give you any explicit example of such n vertex graphs. So you know they exist, you know even most n vertex graphs have this property, but you can't exhibit an explicit example. And in fact, no explicit constructions of such graphs are known. So not just this proof doesn't provide one, but also no, despite a lot of people putting a lot of effort into this, there's no known explicit constructions of such graphs. And even if we make the problem a little bit easier, so even instead of this constant factor 2, we allow ourselves a different constant bigger than 2, which makes this easier to construct. Even then, there are no explicit constructions known for large n. So basically, if you replace this 2 by any other fixed constant c bigger than 2, this problem becomes easier, but there is no constant, even a million, where constructions for this are known for large n. Okay, so this leads to the following definition. So, graphs which exhibit this optimal or maybe up to the constant factor optimal behavior with respect to this Ramsey problem are called Ramsey graphs. So here's the precise definition. So for fixed c bigger than 0, we say that an n vertex graph is called a C Ramsey graph if it does not contain a clique or independent set of size at least c log 2n. So the point here being that these Ramsey graphs, the C Ramsey graphs, they don't have large cliques or independent sets, so they behave kind of optimally with respect to this Ramsey problem. And so, as I just said, there are no explicit constructions known for such C Ramsey graphs for any fixed C and large n. So the larger you make C, the easier it becomes to be a C Ramsey graph. So the easier it should be to construct them, but still for no fixed constant C, there are constructions known, or infinite families of constructions known for this. Okay, and so the problem of finding such explicit constructions is actually closely related to randomness extraction and theoretical computer science. So really there's been, a lot of work on this, and still it seems very difficult to find such constructions. And maybe one reason why it is so difficult to find constructions of such graphs is that it seems to be the case that these C Ramsey graphs must in some sense be random looking. And so, that's obviously not a well-defined thing, but if kind of they are in some sense heuristically random-like, that would explain why it's so hard to find explicit constructions of such graphs. And so in particular, to make this maybe a bit more precise, C Ramsey graphs have various properties which are common for random graphs. So for example, here's an example of such a property. So Erdös and Semaredi proved already a long time ago in 1972 that for any fixed C bigger than 0, the edge density of large C Ramsey graphs is bounded away from 0 and 1. Okay, so what does that mean? That if you, for any fixed C, if you take a large C Ramsey graph then the density, the edge density is at least some epsilon depending on C, and at most 1 minus epsilon, where this epsilon depends on C, but not on N. And so, so that in itself maybe doesn't sound like such a strong statement, right? Because I mean, that just edge density over the overall graph, I mean, that doesn't give you very much information about the graph. But you get much more information if you start applying this theorem to induced subgraphs of the Ramsey graph itself. Because if you have an induced subgraph, so say a vertex subset induced by some vertex subset of at least n to the alpha edge vertices, where again alpha is something fixed, then that induced subgraph will again be a C over alpha Ramsey graph. So that you find that just by basically tautologically from the definition. So basically, if you pass to an induced subgraph, which is not too small, so kind of just say at least n to the alpha vertices by some fixed alpha, you again get a Ramsey graph with a slightly different parameter C. And so that means you can then apply the theorem to this induced subgraph. And so that means the theorem doesn't tell you just something about the overall edge density, but it also tells you that in all induced subgraphs which are not too small, you have density bounded away from 0 and 1. And so that then gives you a much stronger statement about the edge distribution. So not just the overall density, but really in every subgraph, you have an edge density which is bounded away from 0 and 1. And that's a much stronger statement. Okay, so so these types of properties are also typical for random graphs. And so in that sense, that's a random-like property. Erdős also made a series of other conjectures related to kind of the diversity of vertex subsets in C-Ramsey graphs. And all of these conjectures are about basically C-Ramsey graphs having certain properties which are typical for random graphs. And so basically, in some sense, you can interpret that as saying that they must be random-like. Okay, so what does diversity of vertex subsets mean? Okay, that's a very cloudy term, but let me just give one example of such a conjecture. So one of these conjectures, which was proved by Schellach in 1998, stated that every C-Ramsey graph G on n vertices contains 2 to the delta Cn different vertex subsets inducing non-isomorphic subgraphs. So basically this says that there's a very diverse range of induced subgraphs, so kind of exponentially many different induced subgraphs that you can find in the C-Ramsey graph, where here this delta C is some positive constant just depending on C. Okay, and so there was a series of other conjectures, and maybe let me not list them all in detail, but so there was a series of maybe 5 conjectures or something like that, and various of these conjectures have been resolved over the past few decades, but one of the conjectures remained open until recently, and that's a conjecture of Erdös and McKay. And there's no, it's difficult to put a particular year on the conjecture, but in 1992, Erdös had a paper where he listed some of his, his problem papers where he listed some of his favorite problems. And so in this 1992 paper, he said it was an old conjecture of the 2 of them. So it's certainly well before 1992, but he doesn't say from which year it was exactly. But here's what the conjecture states. So it's again a conjecture about C-Ramsey graphs having a certain diversity property of vertex subsets. And so here's the exact statement. So the conjecture states that for every fixed C, there's some positive delta C just depending on C, so that the following holds, namely that for every C-Ramsey graph on n vertices and every integer x between 0 and delta Cn squared, there is a vertex subset of G containing exactly x edges. So basically what the conjecture says is if you give yourself a C-Ramsey graph G on n vertices and any number x, which is reasonable in the sense of not being too large. So in the sense of being at most this delta C times n squared bound, any integer or any non-negative integer up to this bound, then you can always find a vertex subset of G containing exactly x edges. So in other words, you can always find an induced subgraph of G with exactly x edges. Okay, so why is this hard? Well, if it's exactly x vertices, well, okay, this bound kind of wouldn't make sense, but finding an induced subgraph with exactly some number of vertices is basically trivial, right? Because you can just place your vertices as you want in your subgraph, but achieving some exact number of edges is actually not so trivial. So let me maybe illustrate this again with a picture on the next slide, but here Yeah, here I just wanted to mention that. So Erdős included this conjecture actually in several of his collections of his favorite problems, and he also offered a $100 reward for it. So here's again the conjecture, and here is a picture illustrating it. So you have some C Ramsey graph G on n vertices, and some integer x, at least 0 and at most as threshold. And so what you want to do is you want to find a vertex subset of G containing exactly x edges. Okay, so for example, in this picture, let's take x equals 2. And so now what we want to do is we want to find some vertex subset so that inside this vertex subset, there are exactly 2 edges. So here, this is easy. You can take this U, this vertex subset U having exactly 2 edges. But in general, obviously, I mean, for any small example, it's kind of easy to kind of play around with it and find this. But in general, I mean, it's not so easy to find a vertex subset with kind of some prescribed number of edges, because you can maybe try to add vertices one by one. But then whenever you add a vertex, your edge number typically goes up by more than 1. So typically you go up by maybe on the order of n vertices already, edges already. And so you might jump over the x that you're trying to achieve. So then you try to take something out and maybe put something else in, but it's somehow not trivial to achieve this. I mean, yeah. So it's not so clear how you would actually go about achieving a particular number of edges. And so in that sense, the conjecture is maybe somewhat surprising that you can actually achieve exactly that number of edges always. Yeah, so maybe let me also make one more comment about why is there this threshold delta c times n squared makes sense for this x here. Well, obviously for this to be sensible, your whole graph G needs at least this number of edges, delta c times n squared. But that's not a problem, because by this previously mentioned result of Erdös and McKay, we know that the edge density is bounded away from 0, so we know that there's at least delta c prime times n squared edges for some delta c prime bigger than 0. Okay, so this kind of simple plausibility test is certainly passed by this. But that doesn't also, so that tells us there are enough edges in the whole graph that this could be plausibly true, but it doesn't tell us, I mean, it doesn't tell us how to actually achieve each of these numbers up to there. Okay, and so the theorem I want to talk about today is that this conjecture is true. Okay, so maybe let me pause for questions before. So I also tell you about some more results on the next few slides, but maybe let me pause. Are there any questions until now? No questions? That's great. Okay, great. So then let me tell you some more results. So here's again the conjecture. So the conjecture says that whenever I have a C Ramsey graph on n vertices and some integer x, at least 0 and up to this kind of quadratic, reasonable quadratic threshold, then I can find a vertex subset containing exactly x edges. And so our first result is that this conjecture is true. And so here's, let me also mention some previous progress in the direction of this conjecture. So it was previously proved that this is true if G is a random graph. And so that kind of, it goes very much along the lines of kind of this being a random-like property. So for random graphs, this was already established quite a while ago. It was also proved for some smaller range of axes about 20 years ago by Alon-Krivelevich and Sudakov. So they proved that it's true when you let x range from 0 to n to the alpha for some positive alpha depending on C. So basically this threshold is much smaller than this one. So they proved that in some, I mean, let's say some initial small range of x, this conjecture holds. And then it was proved relatively recently by Kwan and Sudakov that G contains quadratically many, so delta c times n squared, many different vertex subsets with distinct number of edges. So basically this in particular tells you that you can achieve all these quadratically many distinct numbers and kind of some sort of initial interval of them. And so what Kwan and Sudakov proved is just that there are many different numbers, but not necessarily this property that it's really some interval, quadratic interval starting at 0. Okay, so this is somehow a weaker version of this, but not really achieving every particular prescribed edge number. Okay, so here's again our theorem where we prove that this conjecture is true, so that we can indeed always find a vertex subset containing exactly x edges in a C Ramsey graph G, and for every x within these bounds. And so, as I just said, a previous result proved this for the smaller range of x from 0 to n to the alpha. And so that means when we want to prove this, we can assume that our x is at least n to the alpha, right? Because the other range, when x is very small, smaller than n to the alpha, is already covered by this previous result. So now we can make another reduction. So I'm skipping over some details here, but this is not somehow a very hard reduction. So we can actually restrict ourselves to an induced subgraph of G, and that way we can assume that X is fairly close to the E of G over 4, where E of G is the total number of edges of G. Okay, so basically, if X is much, much smaller than E of G over 4, so much, much smaller than a quarter of the total number of edges of G, then we can delete a vertex from G, and then X will become a little bit closer to the number of edges divided by 4. And so we can keep doing this. And so as you delete vertices, obviously your edge number jumps. So that way you can never achieve exactly X, but you can get X to be close to the total number of edges divided by 4. Or maybe another way to think about it, you can get the total number of edges close to 4X. So that means, so I'm skipping over the details here, but really this is a rather simple reduction where you really omit vertices and pass to an induced subgraph of G. And so that way you can then assume that X is fairly close to the total number of edges divided by 4. So now let me also introduce another piece of notation. So for a vertex subset U of G, let's with E of U denote the number of edges inside U. And so that means that this notation, what we need to show is that our Ramsey graph G has a vertex subset U where E of U is exactly equal to X. Okay, and so in fact, assuming that X is reasonably close to E of G over 4, what we show is not just that there exists at least one such vertex subset, which is what we need for the conjecture. In fact, what we show is that G has many such vertex subsets. And so how do we do this? Well, we again use the probabilistic method that, that I mentioned earlier. We prove this by showing that a random vertex subset U of G with some reasonably high probability has the property that E of U is X. And so that's why we care about this E of G over 4, because if you take U to be a random vertex subset where you include every vertex independently with probability a half, the expected number of edges is precisely E of G over 4. And so that means what we want to prove is that if X is reasonably close to E of G over 4, then it's reasonably likely that we have this property E of U equals X. So what we need to show is that we have this property with positive probability, because that will tell us that there exists at least one vertex subset with this property, but we actually show a pretty reasonable lower bound on this probability. Okay, so here I'll state this more precisely in just a second, but let me just repeat the setup. So we are in a C-Ramsey graph G. What we want to do is we want to consider a random vertex subset U. And so now what we want to do is we want to study the distribution of this random variable E of U, so of the number of edges inside U. So G is given as a C-Ramsey graph, and U is where the randomness comes from. We include every vertex with probability a half independently, and so that means E of U is a random variable, counting the number of edges inside U. And so what we're now interested in is the event that E of U is exactly equal to some given X. So we're interested in these point probabilities that E of U is exactly equal to X. So E of U is a discrete random variable taking integer values, and we're interested in the probability of attaining a precise point X. And so what we actually prove, so we prove a result where we obtain actually very precise control of these point probabilities. Okay, so here's our result. It's a bit technical, so let me go through it slowly. So the statement's a bit technical, but basically the upshot is that we obtain that we have control very well these how large these point probabilities are. So we have some fixed constant C, and G is a C-Ramsey graph on n vertices. And what we want to do is we want to consider uniformly random vertex subset U, a random subset containing every vertex probability a half. And so what we then prove is that each of these point probabilities, so for every X, the probability of E of U attaining exactly X is at most a constant depending on C times n to the minus 3/2. And we also prove that for every fixed A bigger than 0, and any x which is not too far from E of g over 4, namely at most a times n to the 3/2 away. So basically, every x which is reasonably close to E of g over 4, the point probability is at least a constant, depending on c and this a times n to the minus 3/2, if n is sufficiently large in terms of c and a. So basically what we show is that each of these point probabilities is at most a constant factor times n to the minus 3/2. And if x is reasonably close to E of g over 4, so reasonably close to the expectation of this random variable E of u, then the point probabilities are also each at least of order n to the minus 3/2. So this upper and lower bound on the point probabilities only differ by this constant factor. And so in particular, so here's again the statement, in particular, if x is close to E of g over 4, then it's reasonably likely that we have E of u equals x. So it happens with probability at least of order n to the minus 3/2 if n is large. And so in particular, this probability is positive, and we can show that there exists at least one vertex. So there exists at least one, and there exist in fact many vertex subsets u, so that E of u is equal to x. So that means, so for that reason, this result implies then via the reduction outlined on the previous slides, this conjecture of Erdös and McKay. Okay, and so now so this really looks very complicated, this theorem, but let me just comment a bit more on why there this n to the 3/2 appearing in all these places. So what we care about is this random variable E of u, and we already said that the expectation is E of g over 4. That's why this E of g over 4 appears here. So we want to show that the point probabilities have some reasonable lower bound if x is close to this expectation E of g over 4. So now why do the n to the 3/2 appear in all these places? Well, n to the 3/2 is just the standard deviation of this E of u. So basically what this says is that within a constant number of standard deviations away from the mean, so if x is within a constant number of standard deviations away from this mean, then we show that all the point probabilities are of order 1 over sigma. So basically within this interval, a constant number of standard deviations away from the mean, all point probabilities at least of order 1 over sigma and at most of order 1 over sigma. So that means it's reasonably, so there are no kind of extremely high or extremely low point probabilities within a constant standard number of standard deviations of the mean. So basically the probability distribution looks, the point probabilities look reasonably smooth, but they only differ by constant factors from each other within a constant number of standard deviations away from the mean. So this is kind of, I guess, maybe what you would intuitively expect, but I guess it's this theorem actually proves this, that you don't have any kind of crazy behavior on the point probabilities. Okay, so here's again this theorem resolving the Erdös-McKay conjecture, which we can, via the reduction outlined earlier, deduce from this technical result on the last slide, or from this probabilistic result from the last slide. And so, yeah, so here's again, I guess, our main result that the Erdös-McKay conjecture is true. So this states just as a reminder that for every C Ramsey graph G on n vertices and every integer x between 0 and delta C n squared, there is a vertex subset of G containing exactly this number x of edges. But in fact, we can prove something stronger, namely, so I already commented on why it makes sense to have this quadratic, this delta C times n squared bound here, because the total number of edges of G can be roughly, I mean, it's certainly at least some small constant times n squared, but it might be roughly some small constant times n squared. But it might also be like much larger, right? So it could be that the total number of edges of G is actually much larger than this. And so in fact, we prove a stronger statement than this, namely that every number x almost up to E of G can be achieved as the edge number of an induced subgraph. So we prove a statement where we show that we can achieve every x as a number of edges inside some vertex subset where x ranges almost up to E of G. Okay, so obviously you can't achieve any number x larger than E of G. But so here's the precise version of this. So for every fixed C, if G is a C Ramsey graph on n vertices where n is sufficiently large with respect to C, then for every integer x between 0 and 0.99 times E of G, so up to 99% of the number of edges of G, there is a vertex subset of G containing exactly X edges. And so this is stronger than this, this theorem below is stronger than the one above, because we know by this theorem of Erdös and Semeredi that E of G is at least delta C prime times n squared. Okay, and so the 0.99 here was just some arbitrarily chosen fixed constant less than 1, so you can write the same, so the same statement also holds with any other number strictly less than 1 instead of 0.99. That was just to not introduce yet another variable, to just make the statement more concrete. I put in 99% here, but you can put whatever you want. Okay, any questions?
I have a small one. So is it possible that it could also hold if you put a 1 there, but then just subtract something sublinear?
No, so you can't subtract something sublinear, because so if you have, so it's possible, for example, that all vertex degrees are, say, n over 2. And so that means that you can't achieve any number of edges between E of G and E of G minus n over 2. Mm-hmm. So you need to subtract something at least linear. Oh, okay.
So I meant linear in E of G. Sorry, yeah.
Yes, so that's I think plausible. We haven't really thought about that though, because I guess the paper was already long enough, and really squeezing it from kind of any fixed constant smaller than 1 to something sublinear of E of G. So you can certainly not go by the argument I just said all the way to E of G. I mean, that would maybe be a nice statement you could naively dream of, but that's not going to hold. And now what best possible error term you can put there, we haven't really thought about.
Okay. What are the bounds known on delta prime C?
So I think it's something like on the order of 1 over C, maybe with some log factors or something like that. So it's not some terrible dependence.
So not something too bad. I see.
It's not something too bad.
Thanks. Okay, thanks.
Okay, any other questions? Okay, then let me spend the rest of the time I have to give you a bit of an overview of the proof of our result. So I guess I already told you a bit about, something about the reduction from this probabilistic result to the original Erdös-McKay conjecture. And so now for the rest of the proof, I want to give an overview of the proof of this probabilistic result, which is really kind of the main difficulty to prove this. I mean, the other reductions, maybe a half page or something. So, okay, so here's again this probabilistic result. So you fix C at least 0, and G is a C Ramsey graph on n vertices, and let's assume n is large with respect to C. And so in the following, in all the asymptotic notations, I suppress constants. So these figures will mean kind of up to constant factors, and the indices, and this will mean the constant factors that can depend here on C and here on C and A. And so in particular, because this is kind of asymptotic, let's also assume that n is large with respect to, so let's also suppress in this Wiggle notation that we assume that n is large with respect to these constants C and A. And so now here is what we do. So we consider, we have this C Ramsey graph G on n vertices, and we consider a uniformly random vertex subset U. And we're interested in this random variable E of U, counting the number of edges inside U. We're interested in the point probabilities of this. So in probabilities that E of U is exactly equal to some X. And so the first thing we prove is some upper bound that these point probabilities are at most n to the -3/2. And the second thing is we prove a matching lower bound if X, matching up to constant factors, lower bound if X is reasonably close to E of G. And yeah, maybe let me at this point pause for a second and say, so kind of these sorts of upper bounds on point probabilities. So bounds of this form, I mean, upper bounds on point probabilities are also called anti-concentration bounds. And so that's where the word anti-concentration in the title came from. The title of Anticoncentration and Ramsey Graphs and the proof of the Erdös-McKay Conjecture. So now we know what the Erdös-McKay Conjecture is and what Ramsey Graphs is. And so that was the last bit that was missing. But so basically these sorts of bounds are called anti-concentration bounds, upper bounds on point probabilities. But we also prove these up to constant factor matching lower bounds for these point probabilities. Okay, and then I guess I already mentioned earlier that we do these other terms here. what's the meaning of these other terms? Well, or the relevance. So E of U has mean E of G over 4. That's why this E of G over 4 appears here, and standard deviation of the on the order of n to the 3 halves. That's why the n to the 3 halves appears. And so, okay, so what do we need to show here? Okay, this again, I mean, it's a bit more condensed than the theorem statement earlier, but still looks somewhat technical. But just as an upshot to keep in mind for the following slides, what is our goal? We need to prove an upper bound for all point probabilities, so all probabilities of the form that E of U is equal to some given x. So we need to show that no particular value x is exceedingly likely to be attained by E of U, so by the number of edges inside of U. And we need to show a lower bound for these point probabilities when x is close to E of G over 4. So we need to show that every x close to E of G over 4 is reasonably likely to be attained by E of U. So that's our goal. Okay, so here's again the setup. C is fixed, G is a C Ramsey graph on n vertices where n is large, and we have this uniformly random vertex subset U, and want to prove upper and lower bounds for these point probabilities. So with standard techniques, one can prove that E of U satisfies a central limit theorem. So that means that the large-scale behavior of E of U looks like Gaussian random variables. So if you zoom out a lot, look at it at a very rough large scale, E of U looks like this. Okay, so that's nice, but we need to make a more precise statement, right? We need to study point probabilities. So we need to study this random variable E of U up to a very small scale, up to each individual point. And so is it plausible that this central limit theorem, which tells us basically large scale, when we zoom out a lot, we get this Gaussian picture, can we strengthen this to a local central limit theorem? So that would mean, does kind of E of U also locally look like a Gaussian? So does every point probability up to some small error term look like what we would, I guess, expect in some sort of Gaussian-like behavior? So here's again the setup, and unfortunately, this is not the case. So E of U, if we zoom in a lot, does not satisfy a local central limit theorem anymore. So maybe just to put this into pictures, rather than Gaussian, actually the distribution of E of U can look more like this. So the large scale behavior, if you were to zoom out a lot, still you see this Gaussian, but this Gaussian is overlaid by all these smaller wiggles. And so that means it does not, E of U does not always satisfy a local central limit theorem. And this curve looks crazy, but this can actually happen for E of U. So as I just said, while the large scale behavior is Gaussian, on a small scale, we see the smaller Gaussian-like curves. So, and this means in particular that Fourier analytic methods, which were previously developed to prove local central limit theorems and other somewhat related combinatorial settings, cannot succeed alone here, because just the outcome of these methods would be, the outcome of these methods does not hold, and so in particular the methods can't be succeeding here. And so instead we need to understand the interplay of physical space and Fourier space better. So we can't just apply these Fourier analytic methods by themselves. Okay, and so just because this looks so crazy, just to convince you this actually happens, so here are some histograms from real data. So now what do I mean with real data? I guess I just told you that there are no explicit constructions known of Ramsey graphs, but I also told you that random graphs are Ramsey graphs. So this data was generated by taking a random graph on a large number of vertices, and then from that random graph, so then fixing that random graph, that typical outcome of a random graph, there were many samples of a random subset U taken. I think the picture was maybe 2 million samples or something. So basically you fix your randomly generated graph G, that's highly likely a Ramsey graph, and then you just take random samples for this random subset U. And so now you kind of make a plot for how often does every vertex number appear. And so on this plot on the left side here, you see this Gaussian behavior, but you also see that this kind of, these wiggles we saw on the cartoon in the last picture, you kind of see them here. And if you zoom in more, then you see these wiggles even more clearly. So this picture on the right is a zoomed in version from the picture of the left. And so you really see these wiggles in this strange overlay Gaussian behavior. But it turns so you have this kind of two-scale behavior with this large-scale Gaussian behavior and these smaller Gaussian-like curves overlaid. But it turns out this two-scale behavior can actually only happen if the vertex degree sequence of G is additively structured in a certain sense. And so basically, roughly, the approach of our proof is if we are in this additively structured case, so if we have this additive structure, then we can use this additive structure in our proof. And in the other case, where the degree sequence is not additively structured, this case is easier because then one can basically just apply only Fourier analytic methods by themselves. So we don't have to do this thing of understanding the interplay of physical and Fourier space. So so in this case, in this easier case of the dichotomy where the vertex degree sequence is not additively structured, one can show with Fourier analytic methods that E of U behaves like a Gaussian even on very small scales. So then this two-scale thing doesn't happen. We can show that the behavior is Gaussian-like even at zero.
You only have random graphs as examples. You don't even know whether this last case appears or.
So you mean we don't know whether this last case ever appears? Yeah, I guess that's true. You don't have any explicit examples where this last case appears, but no, actually you can. Sorry, I take this back. You can show that the second case appears by constructing other, so randomized graphs, but not the Erdős training graph model.
You see.
So basically by taking the construction is not super involved, but maybe let me not try to explain it now because it would be a bit of a tangent, but there are some constructions which also use randomness, which gives you Ramsey graphs, and where you can show that for a typical outcome, you're in the second case of the dichotomy. Okay, so so this is roughly the proof approach. So we have this dichotomy between this this additively structured and this additively unstructured case. And so now, because this two-scale behavior is really so strange, let me give you a bit of an intuition or a heuristic why this is actually maybe less crazy than it first seems. So basically, I'm going to give you a heuristic explanation for why this two-scale behavior happens. Okay, so here, so this slide is a bit technical, but I think it's still worth trying to give a glimpse of why this two-scale behavior happens. So we care about this random variable E of U, so the number of edges inside U, and we can write this as a polynomial in the following more or less tautological way. So we can write E of U, that's the total number of edges inside U. So we can write this as a sum of over all edges of G of psi v, psi w, where psi is the indicator vector or the characteristic vector of our random set. So we have this random subset U, and we can consider the characteristic vector, which has ones for all the vertices inside U and zeros for all the other vertices. And so then for every edge VW, psi v times psi w is 1 precisely if V and W are both in U, so precisely if this edge contributes to E of U. And so that therefore, for basically tautological reasons, E of U can be written in this form, which is now a quadratic polynomial in psi. Okay, so far that doesn't seem very helpful. I should say E of G and B of G can denote the edge set and vertex set of G. So far that seems like a tautology that's not very useful. But let's rewrite this again a little bit differently. So rather than considering the ordinary characteristic vector of U, where we put ones for all the vertices in U and zeros for the vertices outside U, let's consider this, let's call it plus minus 1 characteristic vector X of U. So that's the same thing as psi, except that instead of zeros, we use minus ones for the vertices outside U. Okay, and then there's a simple relationship between psi and X. Normally you can check that psi is always X plus 1 over 2. Okay, and so if we plug in this relationship here, so maybe this calculation isn't kind of obvious on the slide, but maybe you can just trust me that by some simple calculation, if you plug this formula in here, then you can simplify and you can write E of U as a polynomial in X. And so this polynomial looks like this. It's E of G over 4, so that's a constant term. It only depends on G. It doesn't depend on X. And then there's some linear part which has this form. So these variables xv have coefficients which are the degrees of the vertices v and g, And then there's a quadratic part, which has this one. So it's, again, some sum over all edges. Okay, so now this looks more complicated. So again, it's maybe not clear why would you do this, because this formula looks more complicated and maybe still not helpful. But actually, if you analyze this now, you see that this is actually somewhat insightful, because the variance of this linear part here, so if you just look at this linear part, you can calculate its variance, and it's on the order of n cubed. But the variance of this quadratic part is only on the order of n squared. So this quadratic part has a smaller variance than the linear part. So that means the linear part dominates the large scale behavior of this random variable E of u. And you can show that this linear part has this Gaussian behavior. Okay, so this linear part has the Gaussian behavior and dominates the large scale behavior. But then this quadratic part basically causes these smaller wiggles. And let's consider the special case where the vertex degrees are all exactly n over 2. So this can actually happen for a Ramsey graph, that all vertex degrees are equal to n over 2. So then this linear part, which we see here, only takes values in n over 8 times z, right? Because, I mean, we have a quarter times a bunch of sums of n over 2s with plus or minus 1 coefficients. So basically, this linear part will be an integer multiple of n over 8. So it has these very discrete spaced out values that this linear part can take. And so while it has overall this sort of Gaussian large scale behavior, it's kind of constrained to the, say, lattice, to these discrete values of multiple integer multiples of n over 8. But so then this quadratic part basically causes some wiggling behavior around each of these points in n over 8 times z. So basically, each of those values that the linear part can take corresponds then to one spike in this kind of funny behavior. So this is kind of where this comes from. And so with this sort of way to look at it, it's maybe now less crazy that this can actually happen. Okay, so this is again this picture which can actually happen. Okay, but so this phenomenon can happen more generally if the degree sequence is additively structured, as I said in this dichotomy. And so I won't give you the precise definition what we mean by additively structured, but let me just mention that to capture this notion of additive structure of this degree sequence, we use the notion of regularized least common denominator, which was introduced by Virchonen in random matrix theory. And so in this additively structured case, we can use this sort of additive structure, which I'm not telling you more about, to find the partition of the vertices in G into a small number of buckets, so that the vertices in the same buckets have similar degrees. So I won't tell you what this regularized least denominator is and what our notion of additively structured is, but but as a corollary of this definition of additively structured, you can show that you can partition the vertex sets of G into a small number of sets. So let's think of these sets as buckets. So we are partitioning the vertices into buckets. So the vertices in the same bucket have similar degrees. So the degrees are not far apart for vertices in the same bucket. Okay, and so in this additively structured case, where we then have this partition into these buckets, we then analyze the distribution of E of u conditioned on the intersection size of this random set u with each bucket. So that means we condition of our random set, how many vertices from each bucket does it take? We condition on that without exposing which the vertices within each bucket actually are. And so that basically corresponds to zooming in and studying the peaks in this toe scale behavior, because it turns out if we condition on these these intersection sizes of u with the buckets, this basically just corresponds to conditioning on, say, zooming into and looking at one of these little peaks in this two-scale behavior. And so these peaks in this picture look like Gaussians, but in fact they're not. So in fact, after conditioning on the intersection sizes of this random set u with these buckets, the distribution of E of u, which in this picture looked like it was just going to be a smaller Gaussian, it can actually look like this. So, so this looks like, I mean, the tip of this maybe looks Gaussian-like, but this is certainly very asymmetric. It's not a Gaussian distribution. Okay, so rather than a Gaussian, the distribution of this E of u after this conditioning is not just a Gaussian, it's a quadratic polynomial of independent Gaussians, it turns out. And so that means in our proof, we need to study study the behavior of quadratic polynomials of independent Gaussian random variables. So, so this is just supposed to give you an idea of why does this come up. And so let me also not say so much more about this, but let me just say that we kind of prove and use several results concerning small ball probabilities of quadratic polynomials of independent Gaussians, assuming that the quadratic form robustly has high rank. And this high rank assumption is actually necessary to prove the desired probability bounds for these quadratic polynomials of independent Gaussians. But so that means that if we now want to apply these tools, so these tools which we develop for these quadratic polynomials of independent Gaussians, we want to now apply them, we need to show that the quadratic forms we're dealing with when looking at these peaks here, they actually have this robust high rank assumption. And so in order to do that, we need to prove that the adjacency matrix of Ramsey graphs satisfies this high rank assumption, which is also a bit technical to state exactly, but so I won't tell you what the exact statement is, but it's something about high rank and robust, I mean, having robustly high rank adjacency matrices of Ramsey graphs. Okay, and so then the Fourier analytic part of our proof, which I also don't want to say very much about, but let me also just say that there are various tools going into that, including decoupling and other techniques, and also combinatorial arguments. Because for different ranges of, we need to study different types of cancellations in the Fourier analytic expressions that occur. So the Fourier analysis part is also not, I mean, it's not so simple. But yeah, so basically this was just trying to give you an overview of the tools which go into this. And so using all these tools mentioned on the previous slides, as well as these Fourier analytic arguments here, we can then analyze the probability of E of U lying in a constant length interval, both in the additively structured case and in this additively unstructured case, which is easier. Okay, so the additively structured case, I mean, is the more difficult and needs these tools like on the last slide with this quadratic polynomials of Gaussians and so on. But yeah, so in both of these cases, we can analyze the probability of this random variable E of U that we care about to lie in a constant length interval, where the length of this constant length interval depends on this constant C from the Ramsey graph. But actually what we need, or what our goal was, to prove upper and lower bounds for E of U being exactly equal to one particular value of X. So basically up to this point, we have upper and lower bounds for E of U being inside some constant length interval. But we want to actually talk about E of U being exactly equal to some particular value X. So for the upper bound, that's not a problem, because tautologically, the probability of achieving exactly one value X is at most the probability of being in this constant length interval. So if you have a good bound on that, we are done. And that in particular implies a good bound on a good upper bound on the probability of being exactly equal to X. But for the lower bound, it's much more problematic. If I just know that with a reasonable probability I land in this interval, how do I show that each of these constantly many points in this interval is actually achieved with a reasonable probability? And so there we need significant additional work. So to get the desired lower bound on these probabilities of being exactly equal to X from these kind of probability of being in a constant length interval, we use something called the switching methods. So roughly speaking, that means we study small perturbations to the random set U, where we take one vertex out and another one in. So we switch one vertex against another one. And so we study the impact that has on this random variable E of U, so on the number of edges, via various combinatorial arguments. But normally when you use the switching method, what you do is you show, well, okay, you want to achieve, say, this X, and you want to achieve this X, and the probabilities are not too different because there's ways to switch one way and the other way. And anyway, then you kind of show that there's at least a certain number of ways to switch, and at most a certain number of ways to switch, and they differ by constant factors, therefore the probabilities differ by constant factors. So this is how you usually use the switching method. But that doesn't seem to work in our setting, so we didn't find any way to find uniform upper and lower bounds on the number of these switches. So instead, what we do is we introduce a novel average version of the switching method, where we consider certain random variables which count the number of switches and then study certain moments of those random variables. And so that way, then we obtain the desired lower bound per point probability. So again, I'm not telling you any details, but I just wanted to give you an overview of the proof. So that's all I wanted to say, and thank you for your attention.
All right, thank you very much for the talk. Are there any questions?
how many of those methods that you all had to piece together were at least partially represented in the previous progress, and or how many of the previous progress methods are entirely useless for the general case?
Yeah, so the previous progress on this particular problem, so on the Erdös-McKay conjecture, the methods were pretty much disjoint from what we are doing, because so the result for x being up to n to the alpha we use as a black box. So we certainly rely on that result, right? Because in our reduction we assume that x is at least n to the alpha. So we use that result, but we don't use their methods, because their method is kind of something completely different. So it's purely combinatorial patching things together. And then the result of Kwan and Sudakov, where they prove that there's at least a certain number of different edge numbers that can be attained in vertex subsets, so at least this quadratic number of different x's that can be attained. That is also so it's also probabilistic. So the arguments share the fact that it's a probabilistic approach, but otherwise they're pretty much disjoint. So this is also purely probabilistic combinatorics and no Fourier analysis and none of these sorts of things. But we do share some ideas with other, I mean, we didn't have to develop everything from scratch. So we use some tools and tricks and similar arguments to what has been in the literature and other problems that have been used, say, especially for the Fourier analysis part. So, these works I have mentioned earlier, not in detail, but I've mentioned the existence where they prove local central limit theorems and somewhat related combinatorial settings with these Fourier analytic methods. So we use part of our argument relies on those sorts of methods and uses a similar approach. But as I said, somehow in our setting, one needs more than that, because that alone can't succeed, because one has this crazy two-scale behavior.
Yeah. Is the reason for using the black box mostly comfort that you don't have to redo it, or is it really an area where your methods just won't work and you really need to patch it together entirely separately?
You mean the black box of the very small x's?
Yeah.
Yeah, so certainly, so our probabilistic approach was, I guess, for x being close to E of g over 4. And that reduction kind of doesn't work anymore if x gets too small, because then you kind of, when you pass to an induced subgraph, that your subgraph would be too small, and so you kind of lose the Ramsey behavior.
Okay.
So I don't know whether there's maybe a way to adapt these methods, but given that this already existed as a black box, we didn't really want to spend additional effort on not using it. So
Fair enough.
I mean, the paper is already 59 pages, so it feels like it was already long enough. And
yeah. Question.
Okay, are there any other questions? Does not seem to be the case. So thank you again, Lisa, for the nice talk.